Aging is often framed as a gradual failure of the body's internal communication systems, where hormonal messages grow weaker, cellular responses become less coordinated, and tissues fall out of sync with one another. This narrative has been used to justify the concept that aging is a disease-like process of irreversible breakdown. But such a conclusion misses a crucial mechanistic detail. The signaling networks that sustain physiological balance are heavily dependent on lipid-soluble vitamins, particularly A, D, E, and K. These nutrients act not merely as cofactors, but as regulators of gene expression, cellular identity, and intercellular communication. When they are chronically deficient, as is common in modern diets and with age-related malabsorption, the breakdown in communication that follows is not mysterious or programmed. It is the predictable result of micronutrient insufficiency. In this light, what we often interpret as intrinsic aging may be more accurately described as a long-standing deficit in the molecular agents of cellular conversation. Vitamin A, as retinoic acid, is essential for cellular differentiation, immune balance, epithelial integrity, and embryonic development. It binds to retinoic acid receptors, RARs, and retinzoid X receptors, RXRs, which directly regulate the transcription of hundreds of genes. These nuclear receptors help cells interpret their environment and determine their fate, whether to proliferate, differentiate, or self-destruct. Without adequate vitamin A, this transcriptional control is disrupted. In aging tissues, such as the skin, lungs, and immune system, we see a characteristic loss of regenerative capacity and structural cohesion. But if the transcriptional machinery is intact and only lacks its vitamin-based ligand, then we are dealing with a deficiency problem, not a fixed degenerative fate. Vitamin D operates through a similar mechanism. Once activated, calcitriol, the hormonal form of vitamin D, binds to the vitamin D receptor, VDR, which then forms a complex with RXR to regulate a broad range of genes related to calcium metabolism, immune function, inflammation control, and cellular growth. Vitamin D status directly influences the function of innate immune cells, T-cell differentiation, and even insulin sensitivity. Deficiency in this vitamin, which is widespread in older adults due to lower sun exposure and reduced skin synthesis, has been linked to frailty, sarcopenia, cardiovascular disease, and neurocognitive decline. Again, the question arises, are these outcomes the result of unstoppable aging? Or are they the systemic effects of long-term hormonal and transcriptional silencing caused by vitamin D inadequacy? Vitamin E, a family of tocopherols and tocotrienols, is often known for its antioxidant properties, but it also modulates cell membrane integrity, gene expression, and signal transduction. It protects polyunsaturated fats in membranes from oxidation, preserving the structure of cellular compartments involved in signaling, such as lipid rafts. Moreover, vitamin E influences key transcription factors like NF-B and AP1, which are central to inflammatory and immune responses. When vitamin E is insufficient, especially in high oxidative environments like the vascular system or the brain, signaling pathways become distorted, leading to chronic inflammation and impaired stress responses. These are key features of biological aging, yet they are often exacerbated or even initiated by the silent degradation of antioxidant defenses caused by nutritional gaps. Vitamin K, especially in its K2 form, menaquinone, adds another layer to this communication narrative. Beyond its classic role in blood clotting, vitamin K is a cofactor for the activation of matrix GLA protein and osteocalcin, proteins that regulate calcium handling in the vascular and skeletal systems. But vitamin K also influences gene transcription through the activation of the SXR, steroid, and xenobiotic receptor, another nuclear receptor. This affects gene networks involved in detoxification, inflammation control, and lipid metabolism. Low vitamin K status has been associated with arterial calcification, osteoporosis, and insulin resistance. These outcomes are not simply wear and tear. They are the physiological expressions of suppressed gene networks, waiting for their nutritional keys. The implications are profound. If the nuclear receptor system, arguably one of the body's most fundamental signaling architectures, is driven by lipid-soluble vitamins, then a deficiency in these compounds creates a systemic communication breakdown. Cells may remain genetically intact, but if their signals are not delivered or received due to a lack of vitamin-based messengers, coordination falters. The body begins to age not because its core systems are irreparably damaged, but because their operational inputs are missing. Furthermore, the interdependence of these vitamins compounds the problem. Vitamins A and D share RXR as a transcriptional partner, meaning that deficiency in one affects the functionality of the other. Vitamin E protects the lipophilic environment necessary for membrane-bound receptors and vitamin storage. Vitamin K ensures proper calcification signaling and may directly modulate bone marrow transcriptional activity. These nutrients form a tightly interwoven regulatory web. Remove any one element for long enough, and the balance begins to unravel, not because time demands it, but because nourishment has faltered. This understanding repositions aging as a complex form of signaling malnutrition. The body does not merely slow down with time. It begins to miscommunicate, respond inappropriately, or fail to act entirely. But this is not an immutable decline. Restoration of lipid-soluble vitamin status through diet, targeted supplementation, and lifestyle changes has been shown to reawaken dormant gene pathways, restore immune surveillance, improve cognition, and enhance tissue resilience. These are not theoretical possibilities. They are measurable outcomes in human studies, especially among older adults whose baseline levels are low. In conclusion, the so-called breakdown in cellular communication that defines aging is, to a significant degree, a consequence of nutritional deficiency, not a fate. Vitamins A, D, E, and K are not optional. They are structural components of the body's internal language. Their absence silences the very instructions that keep tissues coordinated and adaptable. Aging, then, is not a loss of potential, it is a loss of biochemical conversation. And by restoring these foundational nutrients, we restore the clarity, cohesion, and resilience that make vitality possible.